Okay. Just to review, we've been talking about wave functions. And again, I realize that might be kind of a out there concept. The wave function describes the particle slash wave-like behavior of an electron. And actually, you can broaden that definition. The wave function can describe all the particles in a molecule. But for right now, it'll be fine if we just keep the focus on an electron. So some of you have seen the so-called particle in a box system that we maybe talked about last time. Glad you found it. Water bottles are important.
Yes, stay hydrated.
Stay hydrated, everybody. Where if we have a box where inside the box the energy is 0, the potential energy is 0, but outside the box it goes to infinity. And then we allow an electron to occupy all the space in the box, what we would see is that the electron would adopt one of many possible waveforms. One of them involves sort of half a wavelength. If this is x equals 0 and this is x equals a. Another involves a full wavelength. There would be another that would be like 1.5 wavelengths and so on. Maybe don't necessarily want to draw them all on top of each other, so maybe I won't. And I'm putting them at different heights just to indicate that they're at different energy levels. They're not to scale or anything like that. The math has been done here, and doing it by hand isn't that important. But the idea is that the higher in energy you go, the more wavelengths are going to be packed in between this distance. And now I'm getting to the point where my drawing is not accurately representing the math, so whatever. Notice that the wave function goes to 0, so I'll draw a line representing sort of 0 in amplitude. It's kind of weird because on this axis we have energy, but notice that the wave function has no amplitude at either side. The reason for that is potential energy goes to infinity, so the wave function doesn't exist there. But in between that space, it adopts this particular shape. And actually you can, that's just a sine slash cosine function. You can write the math out for that. The wavelength would show up in that, and also an integer describing an energy level, n equals 1, n equals 2, n equals 3, and the energy levels would be related to that. Now there's some principles you can gain from this. One of them is that if you count the number of times a wave function goes through 0, you can order them in order of energy. Notice that the lowest energy wave function, not counting the ends, has 0 times that it passes through 0. We call a place where the wave function passes through 0, we call that a node. And interestingly, though, over time, the wave function will oscillate up and down. The position of those nodes never changes, and the wave function is always 0 at those points. You can count the number of nodes, and that will give you a sense for how high in energy the wave function is. So notice that our lowest energy wave function has 0 nodes, our second highest one has 1 node, and so on, 2 nodes. And notice that this tracks with something that we know about photons and frequency, right? Do you remember that the energy of a photon is directly proportional to its frequency? Higher frequency means higher energy. Same thing with wave functions. You can tell that the frequency is higher because you're packing in more wavefronts in this space. And so as frequency goes up, number of nodes goes up, the energy of the wave function goes up. All right. We talked about some math last time to extract information from wave functions. I want to say just a little bit more about what the wave function means. Most of the time, we're not actually going to write out the math represented by the wave function because it's too complicated, and actually it gets to the point you can't even do it analytically. You need a computer to do it. But one important, there are a few important points. One is that the wave function is a complex number, meaning it can have real and imaginary parts. And so, since anything that we can observe is real, we need to find a way to deal with the fact that the wave function has real and imaginary parts. In math, there's this concept of a complex function having a complex conjugate. I'm not sure if you remember that. It's not particularly important. If A equal, sorry? No, I didn't hear anything. I'm sorry, I thought I heard somebody say something. Excuse me. If we have a function A, which is a real number, plus B times the imaginary unit, its complex conjugate is A minus B times the imaginary unit. And when you multiply a number by its complex conjugate, the imaginary part goes away. So now we're remembering FOIL from junior high. Maybe you remember how to do that. But if you expand this out, you get A squared plus B squared. The imaginary part goes away. And so we're going to do that with the wave function. If we take the complex conjugate of the wave function, and we'll indicate complex conjugate with a little asterisk until we forget to, and then we won't worry about it anymore. But if we multiply the complex conjugate of the wave function by itself, and then we integrate over all space. If this is in one dimension, this would be 0 to infinity dx. That has to equal 1. And last time somebody mentioned, aren't we going to be dealing with wave function squared? What you may have learned before is an oversimplification of what I just showed you, that actually you're taking the complex conjugate of the wave function and integrating it over all space, and that has to equal 1. Now, if you ask what that complex conjugate is at any given point, you'll get probability of finding the electron at that particular point. And when we draw orbitals or wave functions, what we're really drawing is wave function squared within a certain overall probability limit. All right, other questions? Okay. So I want to say a little bit about using operators with wave functions. This is maybe some P-Chem stuff. It's not the most important thing, but it'll help a little bit. As I said last time, once you know what the wave function is, you already know everything there can be known about that particle if you have the right operator. So there's this thing we do in math with wave functions where we can use an operator to extract some detail from the wave function. So suppose I had a wave function describing an electron around a nucleus, and I wanted to know what is the average distance of that electron from the nucleus. I would need a distance operator. And in most cases, these are already discovered for you. The proofs for why they are distance operators are beyond the scope of this class because I don't know. I tried to show you some operator derivations last time, but I confused myself. So you can accept these as fact, as postulates, and if you want to go and look up the proof someday, you can. Turns out the distance operator is just x. Surprisingly. So if our wave function just has one dimension, the distance operator is just x. So in order to determine the average value of x in the wave function, we would take the wave function complex conjugate times the operator applied to the wave function. Now remember, an operator is a function that you can apply to another function. Here the function is just x, so applying it to the wave function is just multiplying it. And then we take all of that and we integrate it over all space. And then we're going to get something called the expectation value for x. That is the average position of the electron throughout all space. You can do this with momentum. Remember, we said the momentum operator P with a little hat is equal to h bar over the imaginary unit d over dx. So if we want to know what we expect for the average momentum of the electron throughout all space, we would simply apply the momentum operator to the wave function. So that's h bar over the imaginary unit, first derivative of the wave function with respect to x. We multiply that by the complex conjugate and integrate that over all space, and we get the momentum. Okay? You can do that with any operator, and you're not going to be doing math to figure out the momentum. You would do this computationally. But that brings us to the most importantest of operators, which is the Hamiltonian operator. And I told you last time that the Schrödinger equation is that if you take this operator and apply it to the wave function, the answer you get out from doing that math is the wave function again, unmodified, multiplied by a scalar number, a scalar quantity, or a number. It's just a number that means energy, which is really kind of cool, right? That there's a function you can apply to the wave function, and it spits out the energy. Yeah.
What units will that energy be in?
What units will that energy be in? It will depend on the constants that you use in the wave function. You can use any arbitrary units. When chemists are dealing with lots of molecules, organic chemists prefer kilocalories per mole. Some of the P chemists like joules for various SI reasons. And then actually when you're dealing with individual molecules, a preferred unit is the Hartree, which is named after a theoretical physicist. So it'll depend, and you can look up the conversion factors. Okay. And in most cases, we're concerned about relative differences, so the units almost don't matter. Yeah. Okay, what else? So I'll show you what the Hamiltonian operator is, and then we'll talk about how the Schrödinger equation constrains the kinds of wave functions that work, because not every function works in this equation. Wave functions that describe real particles have to obey this equation. And so finding out what those wave functions are can be kind of a challenge. But let's talk briefly about what the Hamiltonian looks like. We said last time that the Hamiltonian for a molecule has to account for the following things. First, you've got to account for nuclear kinetic energy. However many nuclei you have, if they have velocity, they also have kinetic energy, and you need to deal with that. Then you need to deal with electron kinetic energy. And then you've got to deal with potential energy, right? The two types of energy a particle can have are potential energy and kinetic energy. So let's deal with the potential energy part of the Hamiltonian. Here you've got first nuclear repulsion. That's just Coulomb's law, like charges repel each other. Then you've got to deal with nuclear electron attraction. And then you have to deal with, and this can get tricky, electron repulsion, which sort of requires you to know all of the positions of all of the electrons always, but then they influence each other's positions. So how are you going to deal with that? And that's why you can't get an analytical solution to the wave function for anything more complicated than a hydrogen atom with one electron. Okay, so let's first make our lives easier. Your text goes and actually writes out all of these terms, I think to scare you into appreciating the fact that they then immediately oversimplify it for you, or simplify it for you. We're going to use something called the Born-Oppenheimer Approximation. Someday, if you do your best and discover things, they can put your name in front of it. So the Born-Oppenheimer Approximation says that nuclei are slow and electrons are fast, so that and the idea behind that is that if the positions of the nuclei change, the electrons can automatically and instantaneously almost rearrange themselves to accommodate that motion. So since we care when we're dealing with a molecule and reactivity, we care most about the electrons, we can actually assume that the nuclei are motionless. We can treat them as though they are motionless. It's not actually true, but on the time scale that's significant for electrons, it just as well be true. So that means that we can eliminate the nuclear kinetic energy term, because we're going to pretend like nuclei are motionless, and if your velocity is 0, then your kinetic energy is 0. We're also going to ignore the nuclear repulsion term. It's not 0, but whatever it is constant and doesn't vary on the time scale of the electrons. And we're doing a lot of calculus here, and you can always factor out constants, so we can ignore that. Okay? So what's left is the three important terms: electron kinetic energy, nuclear electron attraction, and electron-electron repulsion. So let's show you what the simplified Hamiltonian looks like with that in mind. For electron kinetic energy, we're going to have the familiar form that we talked about last time. Little m here is the mass of an electron. And then there's going to be many electrons in the molecule, so we're going to sum all of them to get an overall electron kinetic energy. Total number of electrons, little n, I represents any arbitrary electron. And this upside down delta squared represents the second derivative for an individual electron.
What's it? Oh, that's an N. Never mind. Sorry.
Yeah, sorry.
No, you're good. I thought it was an N.
Penmanship suffers. I need someone to replace my font. Okay, so that handles electron kinetic energy. And then to deal with nuclear electron attraction, we're going to simply use Coulomb's law. So constant K, K is just the constant that comes in front of Coulomb's law. It's 1/4 pi times vacuum permittivity, but who cares? We want to eliminate details, not think about too many. There's going to be multiple electrons and multiple nuclei in our molecule. So Coulomb's law says that the energy between a positively charged nucleus and a negatively charged electron is equal to the product of their charges divided by the radius between them. And then we're going to do that for all of the nuclei. Capital N represents number of nuclei. A represents any arbitrary nucleus. And we're going to do that also for all electrons. Okay, so this is electron nuclear attraction, and it's summed over all the electrons and over all the nuclei. Okay, and this is just...
Okay, sorry.
Go ahead.
Did we eliminate the permittivity of free space?
No, that's in this constant.
Okay.
Yeah. I mean... and the reason I'm doing that is I'm hedging a little bit because you have to not count things twice, and so there may be a factor of 2 in there, and I'm unclear, and somebody deals with that, and it's not me, so I'm just going to use little k.
Cool.
All right. And then lastly, we're going to deal with electron-electron repulsion, and this is going to take the same form as the term above, only it's going to be positive because it's not favorable. It's going to be the charge of electron I and the charge of electron J divided by the radius between I and J. And we'll do that over all possible electrons, but we're going to say an electron does not repel itself. So we'll specify that we're only going to count the interactions between electrons that are different. And we're not going to sum the same repulsion twice, right? If electron I repels J, we're not going to also add the repulsion between J and I because it's the same thing. Yeah. Okay. So, looks simple-ish, right? If you're able to accept what we said about the second derivative being the operator for kinetic energy, this looks like some stuff from physics. All right, we're getting there. Now, with that in mind, what do we do? Well, we have to figure out, this is a differential equation because we're taking the derivative of something and it has to spit out that thing again multiplied by some constant. And as I said before, it's not just any old function that works for this, it's only certain functions that obey this. And the form of the function will depend on the form of the Hamiltonian. Back up here, for the particle in a box, the Hamiltonian is really simple. The Hamiltonian here, you can get rid of any potential energy because there is none inside this box. It's 0. The only thing that matters here is the second derivative of the wave function with respect to that one dimension. And if you solve that differential equation, you get out as an answer those sine/cosine type waves. Okay? So now we're going to do that in 3 dimensions for a molecule. And fortunately, we're going to let the computers do that. But in practice, what we usually do is we come up with a guess for what the wave function is, and then we see what energy it spits out, and then we try to alter the wave function to get down to the lowest energy possible. And I forget what this is called. There's some principle at some point in your text. But the idea is that the calculated energy you give for a wave function always is going to be higher than the actual real energy of the wave function. So for any wave function, as long as you've got the Hamiltonian correct, you get to a lower energy, it's a better answer. So we're going to use that idea. We want to get to the lowest energy possible given the particular Hamiltonian as we solve for the wave function. So we got a molecule, and we know basically what the solutions to the wave functions are for a hydrogen atom, right? That's where our familiar 1s orbital comes from, and the 2s and the 2p orbitals. So when we go to make a wave function for a molecule, and let's just assume still boring molecules, we've got hydrogen A and hydrogen B. How are we going to generate wave functions for that molecule? Well, we're going to say that the wave function for this molecule is a linear combination of the available atomic orbitals from hydrogen A and hydrogen B. So let's see. Hydrogen A comes with a 1s orbital, right? We'll do the same thing with B. I'm using the symbol phi to represent the Greek lowercase equivalent of F. Phi represents the atomic orbital or orbitals that come with an atom in our molecule. We're keeping things simple. The only thing that comes with hydrogen is the 1s orbital in the ground state. So to generate orbitals for a molecule, we're going to do what's called a linear combination of atomic orbitals. We're going to combine atomic orbital A with atomic orbital B. And at this stage, you may be thinking, well, it's obvious they should be combined in a 1-to-1 ratio. But, you know, life can get more complicated. And what if we changed hydrogen to something else? So let's, for the time being, not place that constraint on. And let's say we're going to combine them together in some ratio. There's going to be some coefficient that determines what percent of orbital A and what percent of orbital B contribute to the overall wave function that we observe. One interesting feature of linear combinations of atomic orbitals is that you get more than one orbital out when you mix orbitals together. You get actually as many orbitals out as you mix together. So that's why I put the little I there to indicate that we're going to get out as many orbitals as we put in. Okay, so that's now our description of the wave function for this molecule. And now we're going to try to make it satisfy the Schrödinger equation. All right. So some interesting things about the Schrödinger equation. Here's the operator, here's the wave function, here's energy, here's the wave function. It turns out if we want to isolate energy by itself, it's not quite as simple as dividing by the wave function. Instead, what's done, and they're reaching the limit of my understanding here, I'm not sure. What we do instead is we multiply both sides by the complex conjugate of the wave function, and we integrate over all space. I'm going to stop using x because we're no longer using one-dimensional wave functions. What your book uses for a sort of generic 3D coordinate is the Greek letter tau, as though we needed more of that, but what are you going to do? And then we can factor the energy because it's just the energy is just a constant, so we can factor that out of the integral. And then we can figure out the energy by simply dividing these integrals by each other. A lot of writing here, I apologize. Aren't you glad I'm not just showing this to you on a slide and expecting you to scribble it down as fast as possible? What's going on here? Please say we didn't go to sleep. Okay. At this point, some of you may be asking, hold on. You told us that the wave function multiplied by its complex conjugate integrated over all space was equal to 1, and so I did.
That was what I was going to ask.
Yeah, so I did. But at the beginning, we don't know what these coefficients are, and so this might not be equal to 1. We're actually going to do that after the fact. That's called the normalization process. Now, we get tired in chemistry of writing things. That's why we have skeletal structures for benzene. And people get really lazy. By the way, I don't like, nor will you ever convince me to like that. It makes me mad. That I suppose that's true, and I have to get the circle right too. Yeah. Can you draw a 7-membered ring fast? I had some undergrads when we were talking about aromaticity and how this 7-membered ring is aromatic, and I drew this, and they were like, "That looks like a sad robot." He actually looks kind of smiley at this point, but now looks kind of depressing. So this is called the tropylium cation. It's aromatic and it's sad. So, anyway, we like to abbreviate things. So instead of, sorry, I get distracted. Instead of writing out the integral, we're going to come up with a condensed notation. Hamiltonian goes here. Wave function you apply it to goes here. Complex conjugate goes there. We drop the asterisk and we put the little brackets on there, and that indicates the integral integrated over all space. And we can do that with the integral on the bottom as well. And that's going to equal energy. Okay, yeah.
And operator's always in the middle, right?
Operator's always in the middle if there. You can factor constants out just like you can do in an integral. Operators you can't factor out because they are functions that you apply to other functions. All right, so now it's going to get worse. Is it ever going to get better? Perhaps not, but it definitely will get worse, so hang in there. We said that we're going to let the wave function, we're going to imagine it as a linear combination of the available atomic orbitals. So what I'm going to do now is painful. We're going to plug this in anytime there's a wave function. So I'll write that out here. Energy equals, we're going to take constant times atomic wave function A plus constant B times atomic wave function B. We're going to take the Hamiltonian, we're going to apply it to that wave function, and then we'll multiply it by the stuff out in front. This is exactly what I've shown you here, only we're actually writing out our guess for the wave function. And then we're going to divide that by that integral on the bottom. And yeah, we're going to come back eventually and guarantee that this integral equals 1, but we don't know that now. Okay? Some of you may have done something like this in PChem. I don't want to belabor the algebra, so I'm going to skip a couple of steps ahead. What we basically are going to do is we're going to apply the Hamiltonian to each of those two functions, and then we're going to multiply each of those by this. Okay? So in some ways, you can think of this like the distributive property, and if you do all of that, you come up with the following numerator for our energy. Let's see, no, I didn't want to do that. Sure. Okay, Hamiltonian applied to wave function A times wave function A. And then actually there's going to be CA squared in front of that. Does that make sense? We apply Hamiltonian to this, and then we multiply it by this. Okay. The second term involves the Hamiltonian applied to wave function B, but multiplied by wave function A. And I can see I'm going to run out of space, so I'm going to do what you can't do on paper, which is shrink. And as before, we're going to have CA times CB there. We're going to have another term, CB times CA. This is going to be for the Hamiltonian applied to wave function A, multiplied by wave function B, and integrated over all space. And then the last term here is a CB squared term for the Hamiltonian applied to wave function B, multiplied by wave function B, and integrated over all space. So that's what our numerator is. And the denominator is going to look very similar, only we don't have the Hamiltonians. So there's going to be a CA squared term, which involves wave function A multiplied by itself and integrated over all space. There's going to be a CA CB term with wave function A multiplied by wave function B and integrated over all space. There's a CB CA term with wave function B multiplied by wave function A and integrated over all space. And then lastly, there's a CB squared term. All of these notes are going to be available. So if you're scribbling and you can't quite get all of that down, that's fine. You can see it in the notes. And if you're struggling to see the connection between this and that, you can go back and do the algebra yourself. Now what we're going to do is clean this up a little bit. Okay? We're going to, because we don't like writing out stuff, we're going to make even more brief abbreviations. Okay. So the Hamiltonian applied to wave function A and multiplied by wave function A, we're going to call H double A. And this basically is going to represent the kinetic energy plus potential energy, or we'll just say energy, that's easier, energy of an electron in the starting atomic orbital phi A. Sometimes people call this a core integral. And that's basically just the energy you start out at before you make a bond. Because we can do the same thing for, we can do the same thing for phi B. And again, this would represent the energy of an electron in atomic orbital phi B. But if phi A and phi B are the same kind of orbital and have the same energy to begin with, then we can simplify things by saying that H double A equals H double B. That makes sense. One hydrogen atom is not different from another, so the electron on an isolated hydrogen atom is the same as the electron on an isolated hydrogen atom. Okay. So that takes care of abbreviating this CA squared term and this CB squared term on top. The more interesting terms are what are called resonance integrals. And this is where you apply the Hamiltonian by phi B, but then multiply it by phi A. So let's figure out an abbreviation for that. Checking the time. There's a glare on the clock. We got about 10 minutes left. Okay. So Hamiltonian applied to phi B, multiplied by phi A, and integrated over all space. We're going to call that HAB. And this is going to be what's called a resonance integral. And it's going to describe the energy of an electron shared by phi A and phi B. And I'm not quite sure conceptually how that works out, why when you multiply phi A by the Hamiltonian applied to phi B, you get the energy of an electron shared between those two. But that's sort of how you can think about it. This energy is stabilized. Let's see. So we're going to call that HAB. HAB should be a negative number because it is stabilizing to be shared by two nuclei. That's a potential energy argument, and the electron will have lower kinetic energy between the two nuclei. By the way, HAA and HAB are also negative numbers because it's lower in energy for an electron to be near a positively charged nucleus than to be an infinite distance away. That's our sort of 0 point. All right, because phi A and phi B are identical, it should follow that the other resonance integral HBA, the energy of an electron shared by phi B and phi A, is equal to the first one. Okay? So now we've simplified these two terms, or we've figured out a way to abbreviate them. Now let's deal with the denominator. The integral of phi A multiplied by itself is just 1. Has to be, right? Atomic orbitals, probability of finding an electron in an atomic orbital integrated over all space by definition is 1. And that's the same for phi B times phi B integrated over all space. The weird one, though, is where you have phi A multiplied by phi B and integrated over all space, and similarly phi B multiplied by phi A. These two are called overlap integrals. And they describe the extent to which A and B physically overlap with each other. And it's non-zero when they actually overlap, when they're not orthogonal to each other. Okay? How much the atomic orbitals overlap in space. I'm sorry for the poor penmanship there. So we're going to, because phi A and phi B are the same, we're going to simplify. We're going to call this overlap integral S. I don't know why we chose S, because your book chooses S. Maybe that's because they overlap in space. Starts with an S. I don't know. Okay. So, where are we going with this? Well, we're just trying to make it easy because we're about to do some calculus. So that same expression for energy that I represented above for you, we're going to abbreviate using the definitions we just showed you. Okay. So that's the energy. Notice in none of this have we ever said what the Hamiltonian was. That's kind of convenient. We're just pretending like somebody knows it somewhere and we don't need to know it. All right. Questions so far about definitions or anything you didn't quite get? Yeah.
For the overlap integrals, or like, is there a constructive and destructive interference of them, or?
Good question. Is there constructive and destructive interference? The answer is yes. We're going to get that when we solve the coefficients. There's going to be two solutions and one of them will be positive and one of them will be negative. What else? Okay. So now we're going to, why am I laughing? We're going to simplify this even further with numerator and denominator because we're going to do some calculus, and calculus can be painful. All right. So what we want to do is we want to find coefficients. We can these for the given starting orbitals that we began with, these HAA, HAB, and HBB terms and the S term, we're going to treat like constants. And so we're going to ask the question, how can we choose values of the coefficients CA and CB such that the energy is as small as possible? We want to minimize the energy with respect to the coefficients. Anytime anybody says minimize something, you should be thinking first derivative, because a minimum in a function is where the first derivative equals 0. Also happens to be a max, but we're going to be looking for minima. I'm not sure how we determine whether we've got a minimum or a maximum, but oh well. So what we want to do is take the first derivative of this whole thing with respect to coefficient A and set that equal to 0. And we're going to do the same thing with coefficient B. We're going to ask, basically at that point we'll have two equations and two unknowns, and we will ask what values of CA and CB allow those derivatives to equal 0. So we're going to minimize energy with respect to CA and CB. Okay, so at this point there's some calculus. And there are some notes that I wrote out last year as my pre-lecture notes that I posted on Learning Suite, where you can see how all of that's done. I don't necessarily feel like it's the best use of class time for me to do that because I don't want to. It may or may not be useful to you. I want to show you what the answer is for the derivative of energy with respect to CA. And remember, we're setting that equal to 0. So that's going to equal, for the first one, 2 times CA times HAA plus 2 times CB times HAB minus energy times 2CA plus 2CB times S. Which we can simplify. 0 equals CA times HAA minus energy plus CB times HAB minus E times S. To get from here, oops, I didn't mean that. I wanted the laser pointer. To get from here to here, you just need to know how to take partial derivatives, and you have to remember or look up the quotient rule from calculus. I'll spare you the gory details. If you're comfortable believing that I've done it right, that's fine. You can move on with your life. I don't think it's a useful skill for me to ask you to solve that derivative. This is not a calculus class, and so we can just sort of move on from that. We're going to do the same thing with the derivative with respect to B, and I'll show you that answer next time. We'll have two equations, two unknowns for C and B, and we're going to solve for what CA and CB are. And that will tell us how much of phi A and phi B are involved in the new molecular orbitals that we make. All right, hang in there. It's going to be okay. And I will see you next time.